Using traces and traps in zXDC. Hi, I'm Dave Cole, President of ColeSoft and Chief Architect of the zXDC debugger for assembler programming. In this video, I'm going to show you how to use a zXDC to set traps and to perform execution traces. Okay, let's get started. For the purposes of illustrating traps and execution traces, I'm going to use a program that I wrote a few decades ago. The program's name is SimEdit, and it is a part of the zXDC product distribution. But it is not part of zXDC. It is a separate utility, and its load module can be found here in dbcol.xdcz1d.xdclink, right here. I'm only going to use SimEdit to illustrate some execution trapping and tracing techniques, so what the program actually does is not particularly important. Suffice it to say, SimEdit requires 3 datasets. I'll allocate a sysin input as a dummy. Input dummies contain 0 records, so a GET request just immediately fails over to end-of-file processing. And I'll allocate a syspunch output file, also as a dummy. All records written to it will immediately be discarded. And finally, I'll allocate a sysprint output file as a dummy. Again, all records written to it will immediately be discarded. Notice that in all these allocate commands, I used the reuse operand. This is so I don't have to worry about whether or not the DD name has already been allocated to something else. If it has, then that allocation, whatever it is simply released, and the new allocation is established. Anyway, I'm now ready to start the debugging session. So I'll fill in a program name. I do not need to fill in the program's load library name because this particular program is located in a library that has already been installed into the system's default search order in a linked list, an LPA lib, a job lib, or some such. Now I'll select option 2 on the panel. And now I'm into zXDC. I'll use a where command to display my program. And we see that it is in serious need of mapping. So I'll do that with the M shortcut command, followed by a Q shortcut command to make this the default program, and a where command again to see a much better display. First, I'm going to show you various ways to trace program execution. This is done using certain variations of the trace and trap commands. In zXDC, 3 function keys have been set up for use in execution tracing. They are function keys 9, 10, and 11. Function key 9 just steps through execution from one machine instruction to the next. This is best used when you want to focus carefully on just one local area of code. Function key 10 traces execution from one branch instruction to the next. Actually, it's better than that. It only stops execution on branch instructions that will, in fact, branch. Branch instructions that just fall through are not stopped at. Later, we will explore in detail just how powerful a tracing command, TBY, is. Function key 11 is intended to be used at instructions that call subroutines. Typically, these are BAS, BAL, BAZR, and BALR instructions, and the like. F11 can be used to let the subroutine execute, and then recaptures execution when the subroutine returns. It also can be used at the bottom of loops to allow the loop to run to completion and recapture execution when the loop finally ends by falling through its bottom. Okay, I'll press function key 3 to get back to the code. Single stepping. So let's start with a single stepping trace, just the T command with no operands. That's what's in function key 9. At the moment, execution is stopped at this program's very first instruction, a branch command. Notice that zXDC reports that the branch will in fact occur, and that it will jump execution down to the E013 ZID label. When we press function key 9, the branch instruction will execute, and execution will be recaptured on its target, the store multiple, like so. When we do it again, the store multiple executes and we stop on the load register. And pressing F9 again, execution now proceeds to the load address. Well, that's nice, but it's also pretty slow. TBY, on the other hand, offers a faster way to step through code. TBY is a trace that allows execution to proceed to the next branching instruction that will, in fact, branch. So what's a branching instruction? It's probably more than you think. A branching instruction is any instruction that has the possibility of changing the flow of execution. This pretty much includes all instructions whose names start with the letter B. Conditional branches, branch on counts, branch on indexes, branch and saves, whatever. They also include almost all instructions whose names start with the letter J. Conditional jumps, jumps on count, jumps on indexes, jump and saves, etc. They also include a variety of other instructions not normally thought of as branching instructions, such things as supervisor calls, program calls, load PSWs, and the like. To show this, I'm going to switch to another program of mine that's running on an entirely different computer. This code happens to be using 8-byte wide general registers, so the register display is a bit different here. This code starts off by loading a value into the lower half of wide register 0. But I don't really want to examine this code in detail. I just want to get a general sense of where it goes and if it's doing its job correctly. So I'll use the TBY command to get through it quickly. So let's start. I'll press function key 10 and my first TBY will take me down only a couple of instructions to the jump 0. So now we're about to jump to DSZ 0 check. So let's do that and see what happens. Pressing F10, we now find ourselves down at the jump not equal. Let me pause here and point out several things. To begin with, execution was here at the jump 0, and now it's here at the jump not equal. This means that there are several things that we now know for a fact. First, we know for a fact that the jump 0 did, in fact, branch. So second, we know for a fact that every single instruction between the JZ and its target did not execute. They were skipped. Third, we know for a fact that every single instruction from the branch's target down to, but not including where we are now, has executed exactly once. Not more than once. Not less than once, exactly once. Fourth, we know that every branching instruction within that range has fallen through, has not branched. In fact, zXDC even tells you how many fall-throughs occurred. In this case, there were 3. A branch not positive, a jump equal, and a jump all on. They all fell through. Fifth, the instruction to be executed next is a branching instruction, and it will, in fact, branch. And finally, sixth, zXDC even tells you where that instruction is going to branch to. In this case, a location labeled showz2. 6 things. That's a lot to know from one little command. Well, we don't see showz2 here in the current display, So let's just issue a T command to single step to wherever show Z2 is. And here it is. Pressing F10, the TBY command, we're now down at the JZ. 2 fall throughs have occurred, and we're about to jump to the ER rec label. Say that 5 times fast. And continuing, we can keep pressing TBY for as long as we need to. I'm going to make a few remarks about desk checking. The TBY command is perfect for desk checking new code. When you write a lot of code, a few thousand lines, or even a few hundred, good desk checking technique is critical for code accuracy. Call me old-fashioned, but my first desk checking step is to print out the new code onto paper. Yes, actual paper. Then, with pen in hand, I'll mentally run the new code in my head. This is my first step for seeing that the code actually does what I think it does. And of course, I'll make notes and mark correction points on the paper as I go along. Then I will run the code inside zXDC. When I do, I will use a trap command to place a one-shot trap at the start of the code that I'm interested in debugging that I've just written, and use a go command to let execution reach it. Then I will use a series of TBYs to let execution run through the code and see exactly what has and has not actually executed, and why. Along the way, I will use a highlighter to mark on the printed listing the execution's code path. And if execution deviates from a path that I expect it to take, I will notice that immediately. Now, if there's a piece of code that is skipped but which I want to force to execute, I will use the various zXDC zapping commands to change data, execution locations, and even the code itself to exercise whatever scenario I want to check. So when I am done with desk checking, I will have a high confidence that what I've written does exactly what I think it does. And that's pretty important. All right, let me talk a bit about subroutines, or more specifically, stepping through or over subroutines. When stepping through your code, you may come upon a call to a subroutine. Typically, such a call will be a BAS, BAS, or BAL, or BALR instruction. zXDC, of course, will display the name of the subroutine about to be called. At this point, you have 2 choices. You could decide to continue your execution trace into the subroutine, in which case you'll just continue using T and TBY commands, function keys 9 and 10, just like you've been doing all along. Or you could decide to just let the subroutine run and recapture its execution when it returns. For that, you'll use function key 11. So let's do that. Press F11 and see what happens. Execution was at the branch and save, and execution is now at the load half word. And the LH is the second instruction past the branch and save. What has happened is this. The branch and save has executed. This has allowed the PVT sub-IF subroutine to run. PVT sub-IF has returned to the second instruction past the calling branch and save. And zXDC has recaptured execution there. This, by the way, is why function key 11's command string is so long and complex. The command provides for recapturing execution should the subroutine make what is called a vectored return to any of up to 6 instructions past the calling instruction. Function key 11 works by placing 6 temporary traps onto the 6 instructions following the current instruction. It then issues a go command to let that subroutine run. Eventually, if, and this is an important if the subroutine returns to any of the 6 trapped instructions, execution is recaptured, and all 6 traps are removed. You do have to be aware of the logic of your subroutine and provide for the possibility that it might be designed to return elsewhere. In such a case, you'll have to put traps at those other locations. Alright, I'm going to talk now about tracing through loops. And this is another place in which function key 11 is very useful. First, I'll switch back to the SimEdit program. There's a loop I want to examine down here at sysp search, so I want to stop execution just before the loop. To do that, I'll use the T shortcut command to set a one-shot trap at a place that's a couple of instructions before the loop. Then I'll issue a go command to let execution proceed to the trap. And now we see that execution has been trapped just ahead of the loop. Let me use a W shortcut command to reposition the execution point so it's closer to the top of the display, because I want to do something else down here at the bottom. Alright, execution is about to drop into this loop. It's a small loop running from the sysp search statement down to the branch not equal, about 4 instructions down. The purpose of this loop is to search something called the task IO table to see whether or not a sysprint file has been allocated. The title is no big deal. It's just a simple list of file handles, or DD names, created by the system to identify all datasets currently accessible to the program. I'll set up a new watch window down here so that we can see what the title looks like. And here it is. Oh, okay. It's kind of ugly display, so let's pretty it up a bit. Title map is a script that comes with zXDC that creates a series of equates, or labels, that breaks out the table into its individual entries. It's easy, by the way, to create and run your own scripts. They're just sequential files containing lists of zXDC commands. That's all. Anyway, I'll run the read command, and the script commands are executed and displayed in real time at your terminal as line mode messages. By the way, there is a command for turning off this interrupting display. It's called set no read echo. For now, I'll just press enter and that'll bring us back to the full screen display, where I'll use the where command to restore the primary window's display of the code. And now the watch window shows the same storage as before, but now formatted with equates labeling the starts of each of the title's DD name entries. So let's start running the loop. I'll use function key 10 to issue a tby command to begin the sysprint search. There are several things to notice here. Execution has proceeded from the load at dot plus fox 8 down to the branch not equal at the bottom of the loop. Register 1 has been initialized to point to the start of the DD names list. The first one is for StepLab. The branch not equal is about to cause execution and loop back to the sysp search instruction. On each iteration of the loop, R1 will be advanced down the list. So when we press function 10 again, well, at first blush, nothing seems to happen. But the loop has a run through one pass. What's the evidence of this? Well, if you look closely, you'll see that R1 has changed. It now points to the blank DD name following the StepLab. So we could continue pressing F10 until we finally find the sysprint entry. But titles are often very long lists, and so that could take a while. Instead, what if we simply let the loop run of its own accord until sysprint is found? Well, we can do that in several ways. One is to use function key 11. But F11 can be used here only when two conditions are met. First, execution needs to be at the loop's bottom instruction. Well, that's true here. Second, if the loop has any jump outs, they either must not occur or traps need to be set at the targets of those jump outs. In this case, the only jump out is this BZ instruction. And being the author of this code, I can tell you with some confidence that the BZ will branch only if the list is fully scanned without finding a sysprint entry. But if you recall, we did allocate a sysprint at the beginning of this video, so we don't need to worry about the BZ happening. It won't. So let's go ahead and press function 11 to let the loop run until it finds the tile's sysprint entry. Remember, F11 will place 6 one-shot traps onto 6 locations following the current instruction. And then it will issue a go command to let execution run until one of those traps is reached. Then the traps will all be removed. In this case, the current instruction is the branch not equal at the bottom of the loop. So the first of those traps will go on to the branch and save. The remainder will go on to some inline data that follows the branch and save, thus corrupting the data. But that doesn't matter, because those extra traps are temporary, and as soon as the branch and save is reached, they will all automatically be removed, thus curing the corruption before it matters. Phew! And there you are. We're out of the loop, the sysprint entry has been found, and R1 points to it. More to the point, what you have now seen is this. You have seen how to use function 11 to run a loop and recapture execution when it completes. You have seen how to use F11 to allow a subroutine to run and recapture execution when it returns. You have seen how to use function 10, which is the trace by command, to desk check the execution of new code. And you have seen how to use function 9, the trace command, to step through code one instruction at a time. So what's left? Well, traps. There are different kinds. There are permanent traps and there are one-shot traps. So far, you have seen me use only the one-shot traps. Those are breakpoints that are automatically removed when execution reaches them. Here's an example. I'll use a T shortcut command to place a trap here, then a go command to release execution and let it run until it reaches the trap. And when it does, execution is captured and the trap is removed. This is all very fine. However, sometimes I don't want the trap to be removed. Not until I say so. There can be many reasons for this, but generally I often want to be in a situation where I stop every time execution reaches a breakpoint, not just the first time. So for doing that, there's the at command. AT sets permanent traps that won't be removed until you issue a suitable off command. Here's an example. This program has a subroutine named putMessage. It is called every time this program wants to write a message out to the sysprint file. Well, if you recall, I allocated sysprint as a dummy, so all messages written to it will be discarded and I'll never see them. But I want to see them. Well, here's how. I'll just place a permanent trap at the start of the subroutine that writes all the messages, the putMessage subroutine. Then every time it's called, I can check out the message to be written before it's discarded. I'll start by using the A shortcut command to place a permanent trap on putMessage's first instruction. Now, execution is still way back at .+126, but for our current purposes, it doesn't really matter where execution is. I'll just issue a go command and let it proceed. And pretty quickly, execution winds up here. So what's happened? Execution has been captured by the trap and the trap has not been removed. It's still there. Put message expects register 1 to point to the message to be displayed. So we can just use a format command to see the message. And there it is. I'll use a where command to get back to the code display. Now, using a format command followed by a where command followed by a go command is a little tedious. So going forward, let's create a watch window so that we can see the outgoing message automatically. Remember, watch windows are created by function key 13. A new command line pops up with a suggested command. We'll clear it out and put in the format command that we really want. And there it is. We can see that the first message to be printed by put message is a title message. Now I'll issue a go command to resume execution. The program will proceed along its merry way until it's ready to send another message to sysprint. And that will bring us back to the put message subroutine with a new message to be written out. The permanent trap is doing its job. I can't resist prettying things up a bit, so I'm going to use an equate command to create a label to mark the end of the message. In this program, messages are constructed with a length byte in front of its text. So to find the end of a message, just add its length to the address of its text's first byte. In the equate command, I'll give the label a float attribute so that instead of referencing a static point in storage, the label will float to each message's actual endpoint. When the float operand is used, the assigning address expression is re-resolved every time the equate is used or displayed. In this command, the assigning address expression computes the label's location in terms of the message's address plus its length. And there it is. The message Z label marks the end of the message's text by pointing to the first byte past the text. Okay, let's get back and do another go command. Put message has been called to write out a third message, and so on. And since this is an end of program message, it looks like we're done. So we're done with this trap. But we don't really need to remove it. But we can with an O shortcut command. Okay, that's enough for now. If you have any questions or want additional information, feel free to contact me directly. My email address is dbcole@colesoft.com, and I can be reached by phone at 540-456-6518. We also have a web presence on our own site, and on Facebook, and on YouTube. On YouTube, we have several how-to videos about zXDC. You just might want to take a look at them. Thanks for watching, and I hope this helps. Bye-bye.